Hello and welcome to Mastering Quantum Mechanics Through Problems. My name is Dr. Jacob Hudis. Today I have a great problem for us to look at. It's titled Exploring Quantum Uncertainty with 3x3 Hermetian Angular Momentum Matrices. Let's look at the problem on the next slide.
Let's go.
Here's the setup to the problem. Consider the following 3x3 Hermetian matrices, Lx, Ly, and Lz. Assume that a system is prepared in a properly normalized eigenstate phi that is given in the Lz basis, which is the standard canonical basis, 1, 0, 0, 0, 1, 0, 0, 0, 1. The state phi is equal to sine of theta, 0, cosine of theta. And here's the question. Part A, obtain the average value of Lx, the average value of Lx squared, and the uncertainty in Lx, which is given by the famous standard deviation formula. Part B, do the same thing for Ly, Ly squared, and find the standard deviation in Ly. And for part C, do the same thing for Lz. The uncertainty in Lx quantifies the spread of possible outcomes around the average value of Lx. It shows how much the measurements vary and reflects the intrinsic quantum uncertainty in the system. Part A asks us to find these three quantities.
Terrific!
On this slide, I'm going to focus on finding the average value of Lx. In quantum mechanics, any state phi can always be written as a linear combination of eigenvectors of a Hermitian operator such as Lx, which represents the x component of angular momentum. The Hermitian nature of Lx ensures that eigenvectors form a complete basis and that its eigenvalues are real, corresponding to the possible measurement outcomes. Because Lx is Hermitian, this phi can always be written as linear combinations of eigenvectors of this matrix. Therefore, Lx onto phi is equal to this expression because phi is equal to this expression. These kets are eigenvectors of this matrix, therefore this expression turns into this expression where lambda L are the eigenvalues. This equation tells us that the results of applying Lx onto the state phi is a superposition of each eigenvector, weighted by its corresponding eigenvalue and the amount of the eigenvector present in the state phi. Next, we sandwich this expression with the bra phi. That's done right here. We multiply from the left with the bra phi to find the expectation value. Because phi can be written like this, we replace this phi with this expression, and because of orthogonality, this equation is equal to this. The expectation value, phi Lx phi, is the sum of the possible measurement outcomes, each weighted by the probability of that outcome. This value is, by definition, the average value you would expect if you measure the x component of angular momentum many times on a large number of systems prepared in the eigenstate phi. This approach gives a clear understanding of how quantum measurements work. By expressing the state in terms of eigenvectors of Lx, we can see exactly how each possible measurement outcome contributes to the overall expectation value. That's why this expression is the average value of a quantity in quantum mechanics. So the average value of Lx would be phi Lx onto phi. So the first step is you take the matrix Lx and you act it onto phi, and that gives you this vector. Then you take bra phi, which is just taking the transpose conjugate, and this is a real vector. And then you take this row vector multiplied by this column vector, that's equal to 0, and that tells us that the average value of Lx is equal to 0. Now let's find the average value of Lx squared. To compute the average value of Lx squared, we first need the operator Lx squared. That's the matrix Lx multiplied by Lx. This matrix is Lx squared. Lx squared onto the state vector phi is equal to this new state vector. And then if we want to calculate the average value of Lx squared, or the expectation value of Lx squared, we take the state vector phi and write it as a bra, which means we write it as a row vector. And then we multiply it by this column vector. And when you do this calculation, you find the average value of Lx squared is equal to h bar squared over 2 times 1 plus sine of 2 theta. This involves using a trigonometric identity. So what we have is the average value of Lx equals 0. The average value of Lx squared is equal to this. And then the uncertainty in Lx is equal to the square root of Lx squared, which is this value, minus Lx squared. Well, Lx is 0. Therefore, this is the uncertainty in Lx. I want to stress that calculating expectation values in quantum mechanics involves expressing the state vector as a linear combination of the operator's eigenvectors. Can anyone explain why the average value of Lx is equal to 0? Please just raise your hand. Okay, Serafina.
The average value of Lx represents the expected value of the x component of angular momentum when you measure it. In this case, the average value of Lx being 0 suggests that, on average, when you measure the x component of angular momentum, the result is equally likely to be positive or negative, balancing out to 0. This outcome can happen when the system is symmetrically distributed with respect to the x-axis, meaning there is no preferred direction for the angular momentum along the x-axis. In this particular state, the system has only a plus z component and a minus z component.
Okay, great answer. Waldo, do you know why the expectation value of Lx squared is not 0 even though the average value of Lx is?
The average value of Lx squared measures the average of the square of the x component of angular momentum, which is always a positive quantity because squaring any number gives a non-negative result. This value reflects the spread of possible measurement outcomes. The fact that the average value of Lx squared is not 0 indicates that individual measurements of Lx can still yield non-zero results, even though they average out to 0 over many trials.
Tickle me and call me Elmo.
Great answer.
This is amazing.
Part B says obtain the expectation value of Ly squared, and the standard deviation of Ly. The average value of Ly, also known as the expectation value of Ly, is bra phi Ly ket phi. So you take the state vector phi, you write it as a row vector, and then you take Ly onto phi, and that's a column vector. And if you do that calculation, you get the average value of Ly is equal to 0. The average value of Ly squared is bra phi matrix Ly squared times ket phi, and then if you do that calculation, you get that's h bar squared over 2 times 1 minus sine of 2 theta. So the average value of Ly is 0. The average value of Ly squared is h bar squared over 2, 1 minus sine of 2 theta. And then the quantum mechanical uncertainty in Ly is the square root of Ly squared minus 0 squared. That's equal to this expression. Part C. Obtain the expectation values of Lz squared, and the uncertainty in Lz. You do this calculation the same way. This is how you always do these calculations in quantum mechanics. The average value of L squared works out to be negative h bar cosine of 2 theta. It's not 0 in this case. Lz has some amount in the plus and some amount in the negative direction. Lz squared is equal to h bar squared, and the uncertainty in Lz is equal to h bar times the absolute value of sine of 2 theta. On this slide, I have the quantum mechanical uncertainties in Lx, Ly, and Lz. These are the expressions we just worked out. In this problem, the uncertainty principle demonstrates that the angular momentum components Lx, Ly, and Lz cannot be precisely known simultaneously. For example, when theta is equal to pi over 2, the uncertainty in Lz is 0. There is no uncertainty in Lz, meaning it is precisely known. However, the other two components, Lx and Ly, have non-zero uncertainty. This interdependence is a direct consequence of the non-commuting nature of the angular momentum operators, reflecting the fundamental limits of measurement in quantum mechanics. acephysics.org. Math and Physics Tutoring with Dr. H. acephysics.org. Math and Physics Tutoring with Dr. Hudis.